Welcome back. This is the second video in a series that make up the self-paced Arduino Motion workshop. I'm Lauren, your workshop guide. Previously, we did an exercise hooking up a DC motor to the Arduino UNO using a push-button switch where you decided when the motor would be on or off. If this doesn't sound familiar, navigate back to our Canvas page and start with the first workshop video. In this video, we're going to work with a new piece of hardware and code that will allow the Arduino to be the one in control. Now that we've spent some time using a push-button switch to control when the DC motor is on and off, let's use a new component, the transistor, which can mimic that same switching behavior, but we can use the Arduino to tell it when to turn the switch on and off. This component has 3 pins, a collector, a base, and an emitter. When a high signal is put on the base pin, it allows current to flow between the collector and the emitter pins. We can use this as a switch where the Arduino controls the base pin. That transistor we just spoke of can physically replace the same location on the board as the push button. The middle pin simply needs to be sent to the Arduino to control whether or not the Arduino turns the motor on or off. So let's swap out our push button for the new transistor. In order to do so, let's lay out our components. First, the transistor, taking care to make sure that the numbers and markings on the casing reflect a transistor component, our 330 ohm resistor, and a jumper wire to get communication controls from the Arduino back to the breadboard. Speaking of the Arduino, why don't we just go ahead and remove it from our breadboard for right now. Let me pry this push button off the breadboard real quick here. Let me tell you, that thing was quite secure from our previous exercise. Now that the space is clear, I need to place the transistor on the right-hand side of the breadboard. This way, it leaves room on our breadboard for the resistor to be placed across the center line. Next, place the resistor and make sure that it is in the same node as the base pin or middle pin of the transistor. Now, let's relocate the wires that were previously attached to the push button to the transistor. The black ground wire needs to be placed on the emitter of the transistor, and the green power wire needs to be placed on the collector of the transistor. Take care to make sure that they are in the correct row or the circuit will not work. So let's reintroduce our Arduino to the new circuit on our breadboard. Remember, the whole point of this is that the Arduino is now controlling the motor. We're more or less hands-off. This is why the node on the 7th row with the resistor lead goes to the Arduino pin. This is what will control the spinning of our motor. Now, the last thing that we need to do is apply power and ground to our circuit. So we're just going to take the same power and ground leads from our Arduino and plug them into the power rail on our breadboard. Now if you remember, we have code already loaded onto our Arduino. That code was to blink an LED on pin 13. Technically, those are the only commands that we need, so plugging in our Arduino, we should immediately be able to hear the whir of the motor from the spinning of the LED commands. So let's listen in. If your motor doesn't run, check your transistor circuit and make sure it's plugged in the correct direction. And once you're ready, let's keep moving. Starting with your blink code, see if you can't control the speed of your motor using only digital write and delay within your code. See if you can't control it at half speed, quarter speed, and 3/4 speed. If you need some help, check out the SparkFun Inventor's Kit guide, circuit number 12, as a better resource for understanding how this all works together. And if you finish early, see if you can make the motor spin the other way, as well as determine the minimum speed for your motor. The speed of a DC motor varies with voltage. However, we know that the Arduino only produces a digital signal, a high meaning 5 volts and a low meaning 0 volts. So how do we get something in between only using code? The trick is to change your delays so that they're very small. At the computer level, they'll be processed so quickly that the average voltage over the time that we're changing the signal from high to low is interpreted as a fraction of the total voltage given. This concept is known as a duty cycle. In our case, our duty cycle is 25%, 1 millisecond spent high out of 4 total milliseconds in the cycle. A duty cycle should not be confused with the frequency. The frequency is 1 over the total time spent over a period. If we, let's say as a mind exercise, double our time spent in delay, our time spent high is now 2 milliseconds, and our time spent low is now 6 milliseconds. The duty cycle is still 25%, 2 milliseconds out of a total of 8, but the frequency has just been halved. You might be thinking to yourself, this sounds terrible. I don't want to do millisecond math every time I need to spin a motor at a lower rate. And you have every right to feel that way. It's awful. The good news is that someone else already put together an easier way to accomplish this very thing. It's just important that you know what's physically happening to your hardware when we use these commands. Which is what exactly? We're producing a voltage that is somewhere in between 0 and 5 volts. Remember, when I'm thinking digital, you're thinking all or nothing, exactly. And when looking for a signal somewhere in between, you should be thinking analog. Let's review our arsenal of commands. In the digital world, we've used digital write and read. And in Intro to Arduino, remember we used the command analog read to read in a changing voltage value from a photocell. So what's left? Analog write. Analog write is what we just did. We manipulated the duty cycle and frequency of digital write to get a value in between, and that manipulation is called pulse width modulation, or PWM for short. Now take a look at your Arduino again. Do you see anything that suggests your Arduino can pulse width modulate? I see PWM tilde in parenthesis next to digital. Notice how some of the pin numbers have a tilde as well? Those are the digital pins that are equipped to be able to perform the command analog write. Analog write can accept any whole number integer value, from 0 up to 255. This is a limitation of the hardware. 2 to the 8 bits is 256, or 0 to 255 total values, but that's a discussion for another day. If analog write 0 is a 0% duty cycle, and analog write 255 is a 100% duty cycle, what signal will each of them produce? And what digital command will produce the same signal? A 0% duty cycle is never on, and a 100% duty cycle is always on. You might recognize these as digital write low and digital write high, respectively. Each of the other numbers scales linearly between 0 and 5 volts. Example, 2.5 volts would be 255 divided by 2, or analog write of 127. Remember, this doesn't operate in decimal values. Let's use this new command to change your blank code. Start by changing your pin to one with a tilde. Next, write values to your motor starting around 60-ish and going up or down until you find the minimum value to start your DC motor. If it's humming, it's very close, but remember, you want to find the minimum value where it starts on its own. Now that you have the lowest value for your motor to turn on, determine its 1/3 speed and 3/4 speed values. Then run it through a loop of full, 1/3, 3/4, and then off speed for 2, 3, 3, and 2 seconds respectively. Once you've mastered that, challenge yourself to increment from off to full speed and then back down again using a for loop. Now that you know these tools, is there any way that you know of that you can make the motor change its direction? So let's talk through the code that makes my motor spin. I determined the minimum value for my motor to turn on was 53, or just over 1 volt. From there, the range of my values between 53 and 255 correspond to 123 for 1/3 the total speed, and 205 for 3/4 of the total speed. Here's a video with a small tape flag on my motor sprocket to try and help you distinguish the phases of each chunk of my code. Feel free to continue experimenting controlling the DC motor using analog write in your Arduino. See if you can complete the challenge exercise of revving your motor using the for loop. But for now, this concludes the second video of our self-paced Arduino Motion workshop. Join us in the next video where we'll learn how to use the same concepts of PWM, but this time controlling servos.